Welcome back, focused learners, to today's explainer. We're jumping straight into something that literally separates the guessers from the masters in the scanning room: ultrasound physics. We often think of great clinical imaging as an art form, but really, it's hardcore science. Image quality isn't about luck, it's physics in action. Okay, let's dive into this. Have you ever wondered why two identical machines, plugged into the exact same wall, using the exact same settings, can spit out totally different images depending on who's holding the probe? Well, it all comes down to wave mechanics. Every blurred border, every missed margin, or hazy image traces back to a wave property that you, as the operator, can control right there at the console. Let's demystify the physics behind every single image you generate. So, here's our game plan for today. 5 quick chapters: anatomy of a wave, sound meets human tissue, the golden trade-off, shaping the beam, and we'll wrap up with motion, artifacts, and safety. Let's get to it. Chapter 1, Anatomy of a Wave. Let's start right at the beginning, deep inside the machine. First off, we need to remember what ultrasound actually is. At its core, it's a mechanical pressure wave. That means it needs a physical medium to travel through. And the best part? It is entirely free of ionizing radiation, making it incredibly safe compared to things like CT scans. Now, human ears, we top out at hearing frequencies around 20 kilohertz, but diagnostic ultrasound operates way, way above that. We're talking between 2 and 15 megahertz, literally millions of cycles per second. Now, every single sound wave you create is defined by 4 key numbers: frequency, wavelength, propagation speed, and period. But the absolute most critical relationship you need to lock into your brain here is the one between frequency and wavelength. When you crank up the frequency on your console, you automatically shorten the wavelength of that sound wave. Why do we care? Because a shorter wavelength is your golden ticket to unlocking ultra-fine image detail. So the crucial point is that this whole relationship is governed by the speed of sound. In human soft tissue, propagation speed is mathematically locked in at roughly 1,540 meters per second. To put that in perspective, that's more than 4 times the speed of sound in air. And because this speed doesn't budge, your frequency and wavelength are essentially locked in a dance. If one goes up, the other absolutely has to go down. This fixed speed is the very foundation that dictates exactly how much detail you can pull out of an image. But how do we actually make these high-frequency waves? Well, it happens through this fascinating microstory called the piezoelectric effect. Inside your probe, there are these tiny crystals. When the machine zaps them with an electrical voltage, they physically flex and shudder, firing a mechanical sound pulse straight into the patient's tissue. And then, the magic happens. The probe stops transmitting and just waits. When the echo bounces back from the tissue, it hits those exact same crystals, physically flexing them again. This compression creates a tiny electric signal that the machine can actually read. It's crazy to think about, but your probe spends almost all of its time just quietly listening, using the microsecond time delays of those returning echoes to calculate the exact depth of the tissue. Let's move to Chapter 2, Sound Meets Human Tissue. We'll track that wave right as it leaves the probe and enters the body. Once that sound enters the body, it's going to hit different tissues, right? And this is where acoustic impedance comes into play. Think of impedance as just tissue density multiplied by the speed of sound. An echo is only born at the boundary where that impedance changes. If you have a mild mismatch, like say fat sitting next to muscle, the boundary bounces a small, delicate signal back to the probe and lets the rest of the sound wave pass right through to see the deeper stuff. But if you hit a massive mismatch, like soft tissue directly against bone or air, that boundary acts like a total brick wall. It reflects almost everything right back. This is exactly why we absolutely have to use ultrasound gel to kill that air gap between the probe and the skin. And it's also why dense bone leaves a massive dark shadow right behind it. Now, as the wave travels through all these tissues, it gets tired. We call this attenuation. Sound naturally loses energy as it pushes deeper into the body, losing roughly 0.5 decibels per centimeter per megahertz. The big takeaway for you here: higher frequencies attenuate or lose their energy way, way faster than lower frequencies. Which leads us perfectly into Chapter 3, the golden trade-off. This is the core conflict of all ultrasound imaging. To really grasp this trade-off, we have to talk about resolution, which basically comes in 2 flavors. First up is axial resolution. This is your ability to see detail vertically, right along the beam path. For brilliant axial resolution, you need shorter pulses, which means, you guessed it, higher frequency. Second is lateral resolution. This is your side-to-side detail, perpendicular to the beam. Lateral resolution depends entirely on the width of your beam, and your beam is at its absolute narrowest and finest right at your focal zone. This is exactly why you must always keep your focus markers set at the exact depth of whatever lesion or organ you're evaluating. And this brilliantly illustrates the ultimate rule of transducer selection. It's the inescapable balance between depth and detail. Look, if you choose a high-frequency probe, you're rewarded with brilliant, crisp resolution. But because it attenuates so quickly, your penetration is going to be incredibly poor. It's fantastic for superficial stuff like thyroid, vascular work, or MSK. But if you need to see deep into the abdomen, you have to switch to a low-frequency probe. You give up that crisp, fine detail, but you gain the deep penetration you absolutely need for abdominal or OB/GYN exams. You simply cannot have both at once. Chapter 4, Shaping the Beam. Let's see how modern tech actually controls and displays all these returning echoes. You know, in the early days of ultrasound, probes actually had tiny, physical, moving parts inside them to literally sweep the beam back and forth. No joke. Today, we use electronic beamforming. The machine fires those hundreds of tiny piezoelectric crystals in highly specific microsecond delay patterns. By just tweaking the exact timing of when each individual crystal fires, the machine can steer, sweep, and focus the sound beam entirely electronically. Not a single moving part required. And this electronic wizardry allows us to use different probe shapes for different anatomical jobs. You're going to grab a flat linear array for superficial, high-resolution detail. You'll switch to a curvilinear probe for those wide, deep abdominal views. Got a tight acoustic window, like right between the ribs for cardiac? You need the tiny footprint of a phased array. And for close proximity pelvic imaging, you're using an endocavitary probe. But here's the coolest part. Whether you tell the machine to show you the data as a simple A-mode spike, a standard grayscale B-mode image, or a motion-tracking M-mode line, the underlying physical pulse and echo principle remains exactly the same across the board. Now, we arrive at our fifth and final chapter, Motion, Artifacts, and Safety. Let's bring it all together. So when sound bounces off a stationary organ, the frequency that comes back is the exact same one that went in. But when sound bounces off moving blood cells, the returning frequency actually shifts. This is the famous Doppler shift. But listen up, here is a critical warning for your daily practice. Doppler physics rely heavily on your angle of insonation. You have to try and keep your ultrasound beam as parallel to the blood flow as possible, ideally keeping it under a 60-degree angle. If you approach a 90-degree perpendicular angle, your velocity accuracy just falls right off a cliff towards zero, and the machine will flat out lie to you and say there is no blood flow at all. Depending on the specific clinical question you're trying to answer, you've got three main tools. Turn on color Doppler when you just need a quick read on the mean direction and presence of flow. Deploy Spectral Doppler when you need highly precise quantitative velocity waveforms to measure things like stenosis. And if you're hunting for tiny vessels with incredibly slow flow, go with Power Doppler. It ignores direction entirely just to give you maximum sensitivity for low flow states. Now, what's really interesting about this concept is how it fundamentally changes our mindset. It's so easy to get frustrated by image glitches, but a master sonographer lives by this rule. Never view artifacts as errors. They are physical clues. Seriously, artifacts are just sound waves interacting in totally predictable ways with extreme anatomy. Let's contrast two incredibly common ones to show you what I mean. Acoustic shadowing drops a huge dark void behind a structure. That's not an error, it's a massive diagnostic clue proving the structure is highly dense or calcified, like a gallstone. On the flip side, posterior enhancement throws a bright white spotlight behind a structure. That proves the sound traveled through that area with zero resistance, essentially confirming you're looking at a fluid-filled cyst. Even reverberation and mirror artifacts aren't glitches. They're just showing you exactly how sound is bouncing back and forth across strong reflectors in that specific patient. You're basically acting as an acoustic detective. But while we're having fun manipulating all this physics, patient safety remains absolutely paramount. Yes, ultrasound is exceptionally safe, but it's still depositing acoustic energy into human tissue, which can cause microscopic heating or cavitation. We absolutely must follow the ALRA principle, as low as reasonably achievable. Only use the power and scanning time necessary to get your diagnostic answer. Always keep an eye on your thermal index, or TI, and your mechanical index, or MI, right there on the screen, especially when you're doing delicate early obstetric scans. All right, let's wrap this up and summarize the key takeaways from today's explainer. Number 1, choosing your frequency is always going to be a strict compromise between fine detail and deep penetration. Number 2, adjusting your focal zone is the #1 way you improve your lateral resolution. Number 3, those weird shadows and bright spots, they're artifacts handing you crucial diagnostic context. And finally, practicing ALA keeps your patients safe while you investigate. At the end of the day, every single knob on your console is just a tool to manipulate wave mechanics. Mastering these physics translates directly into crisper images and ultimately much better clinical care. So I'll leave you with this final thought. The next time you walk into the scanning room and pick up that probe, will you rely on guesswork, or will you command the physics of the sound wave? Thank you for exploring the science of sound with me today. Keep practicing, keep analyzing, and we'll catch you in the next explainer.